A logarithm undoes a variable. Should I write it in? A logarithm, what does it do? What's its purpose? A logarithm undoes a variable when it is in the exponent. So it's an operation. It undoes stuff. That's how you solve for a variable. What undoes multiplication? What undoes addition? What undoes this, Berto? What undoes a square? A square root. But what's the difference between x squared and 2 to the x? This guy right here.
The variable is the exponent.
Okay, now you see how the variable is in the exponent spot? If you have to solve an equation and your variable is in the exponent spot, the only way to undo a variable when it's in the exponent is to do a logarithm. So a logarithm is just something that undoes. And we call that an inverse. It's an inverse operation. Like the inverse of times is divide, the inverse of add is subtract. It's the inverse of exponentiation. Okay, let's make a table and graph this function.
1.
If you plug in a -1,
1.
what's 2 raised to the -1? Should be 0.5. If you've got 2 raised to the -1, it should be 1 over 2 to the 1, which is just 1/2, so 0.5. What do you get if you plug in 0? 0 is going to give you 1. What's 1 going to give you? 1's going to give you 2. What's 2 going to give you? Alright, now, here's a grid. Graph it. How are you going to graph it? Where do you want to put your x-axis and y-axis? The middle? Should we just go down the middle? Alright. What did you say, Shania? Alright, if we go down the middle. Yeah, you're free to choose how you want. If we go down the middle, this dot, -2 and up a quarter is not very much. -1 up halfway. 0 up 1. Over 1 up 2. Over 2 up 4. If you connect those dots, what's it going to look like? Bertel, what's the line going to look like? It's growing? It's exponential. If it keeps going, it's going to take a... What if it keeps going to the left? What's it going to look like to the left? Where is this line going to end up? It never crosses the x-axis. It's going to get closer and closer and smaller, but it will never touch the x-axis, and it will never ever go below. Why? Because if you go this way, you're growing. If you go this way, you're shrinking. If you start off with a buck and you divide it by 2, and you divide it by 2 and divide it by 2, remember that? You're dividing something by 2, and no matter how big the amount is, if you cut it in half, do you still have an amount? You can, even if it's microscopic and you divide it in half, you're going to still have something. So you can never ever go and have some input that's going to give you 0 or a negative. Okay, let's do the inverse. Let's look at this guy. Here's your original function, y equals 2 to the x. How do you find the inverse of that? Huh? Oh, that's good, but no. What's the first step, Melody? How do you find the inverse? What's step number 1? Starts to switch. Switch your x's and your y's. So you go x equals 2 to the y. Do you remember that? Ty? Does that ring a bell? To find the inverse, all you do is switch your x's and y's. Now what's step number 2? Solve for? You got to solve for y. Now Danny, y is in a tricky spot. Y is in the exponent. How are you going to undo that? Who said it? Derek. So let's undo it. The only way to undo it if it's in the exponent. This right here is the whole purpose of a logarithm. So what's it going to be? Derek? It's going to be log of what? Log, what's the base? Log in base 2 of x equals, sweet, you just did it. Look what you just did. You just got y out of the exponent, Bertel. You got y all by itself. You got y out of there. That's sweet. So Bertel, what's the inverse of y equals 2 to the x? What is it? Y equals log in base 2 of x. These two things are opposite. They're inverse. All you do to find the inverse is switch your x and your y, and then you solve for y. Okay, let's make a table. Here we go. Ty, here's a problem. This, if I plug in something for x and then I do log base 2 of that, that's going to suck. So let's go back to this guy right here. Now the rule says x is equal to 2 raised to the y. So do you want to plug in for x or do you want to plug in for y? Y. You're going to plug in for y. What do you want to plug in for y? Let's plug in a -1. So we're kind of going backwards. If you plug in a -1 for y, Jake, what does it spit out? What's x? If you plug a -1 in for y, what does it spit out? 0.5. What else do you want to plug in?
0.
You plug in 0 for y, what's it spit out? What else do you want to plug in? If you plug in 1 for y, what does it spit out? If you plug, let's plug 2 more in. What should we plug in? If you plug a 4 in, plug a 2 in.
You get a 4.
If you plug a 3 in, it gives you a, what does it give you? 8. Plug it in for y.
Oh,
Because the rule is backwards. Okay, now what do you notice about these tables? They're the same, but how are they different? They're just the domain and range are switched. Look at all your x's become all your y's, which is the inverse. What do we do to find the inverse? You just switch your x and y, right? So all you do is switch your table. All your x's become your y's. Let's graph it and look. Let's graph it. Let's go right down the middle again and start plotting your points, and let's have a look and see what they look like. Negative or over 0.5, down 1, over 1 and 0, over 2 and up 1, over 4, up 2, over 8 and up 3 is going to be somewhere like right here. So your line is going to go to the right. It's going to keep going up. What about to the left? What happens if it goes to the left? It's going to go down. Is it ever going to cross this axis?
No.
It's going to get closer and closer and closer. Okay, let's do it. Logarithms are brother and sister with powers, exponents. Just like times and divide are brother sister, right? So logarithms are married to powers. Come down to this product of powers property. Here are all the rules for powers. Shania, there's a typo. You got to change this. This product of powers should be x squared. Change it to times. It should be times x cubed. So if you're multiplying two powers with the same base, do you remember what to do with the exponents? You change it to x2 plus 3, right? And you can go backwards. If I have this, if I have x to the 21, can I rewrite that as x to the 20 times x? You can go backwards. Okay, the property that matches with logarithms is this. Let's write this in. So straight across from here, here's our property that matches up with logarithms. If you have the log, and let's just say we're all in base 10. So Ezra, write it down. If you got the log in base 10 of 4 times x, how can I rewrite that? Irvin, you remember how to rewrite that? If I'm taking the log of the product of two factors, how can I rewrite it? Log in base 10, 4 plus log in base 10 of x. So you're taking one log and you're separating into two logs, and they're separated by a plus sign. Do you remember that? And that is the mirror of the product property of powers. Okay, let's do the quotient. Do you remember this quotient property of powers? If you're dividing them, what do you do with the exponents? Okay, let's do a log. Morgan? Let's write log in base 10. Let's do of 4 divided by x. So now I'm taking the log of a fraction. What does the property say you can rewrite it? Log in base 10 of 4 minus log in base 10 of x. Berto? X, yeah. So you can take one log and you can separate it into two logs. And if you're taking the log of a fraction, you separate it with a minus, subtraction. Okay, this is the one we've been using all morning long. What about the power property of logarithms? What if you're taking the log in base 10 of x to the 4th? What if you're taking the log of a power? What do you do then? How do you rewrite it? You bring the exponent out front. So Sierra is going to be 4 times the log in base 10 of x. Or you can go backwards. If they give you this, you can rewrite it as that, right? Okay, those are the three main ones. What if you have a negative exponent? What do you do there? So what about if you're taking the log? What if I'm taking the log in base 10 of a negative 4? Berto, what happens if I have a negative I need to take a log of? What is this problem asking you? Let's change it to exponential. Ezra, what's the base? What's the exponent? What does it equal? Here's my logarithm. What's the base? What's the exponent? What does it equal? Base is, where does the negative 4 go? Here or here? Negative 4 goes here. So my question is this. What exponent is going to give you a negative 4 when the base is 10? Morgan, I'm asking you, when is this line going to go down into the negative? Never. It's never. This line right here is never going to go down into the negative. Sweet. Your answer to this is no solution. You can never, ever, ever have a log of a negative number. What about this, Melody? Can you take the log in base 10 of 0? Can it ever equal 0? That is also no solution. Your graph is never going to touch the x-axis, and it's never going to go below. It's impossible to get a 0 or a negative.
So if you just put it in your calculator, it'll say error.
Let's do it. Let's take the log in base 10 of a negative 4.
Say non-real numbers.
It's going to say error. Non-real answer. Good, Morgan. Okay, last one. Do you remember there's a rule if you got 0 for an exponent? What's anything to the 0 power? 1. Okay, let me erase. So the rule for logarithms is going to be this. What if you have the log of in base 10 of x equals 0? Alright, let's change it. Jake, give me the base, give me the exponent, give me the what it equals. What's the base? 10? Where does the x go? X? What about, where does the 0 go? So what is 10 to the 0? So what's x? X has to be 1, right? If your log is ever equal to 0, that means 0 is the exponent, so your answer's got to be 1. Okay, read through this and answer this question right here, number 1. Okay, E, from here on out, this letter, and it's going to be kind of in italics, E is a number, just like pi is a number, just like I is a number. When do you use pi? When is pi used?
Circles.
Pi is used with circles. When is E used?
Exponential growth and exponential.
Alright, box it. See that? Put a box around this guy right here. E shows up when you're doing exponents. E shows up especially when you're looking at exponential growth and exponential decay. Logan, what's exponential growth or exponential decay?
How much the line goes up.
So growth would start like this. It might start small, but then it's going to grow and it's going to take off. What would decay look like?
Decay or ratio.
It's going to start high and then it's going to decay rapidly, and then pretty much it's going to slow down and not decay so much. Always.
Okay, isn't it if your number that's touching the exponent is less than 1, it's always going to decay? But if it's more than 1?
Nice. Good job. Shania? Okay, let's say what Shania said. If your exponent, so there's your base. If your exponent is what, it's going to decay.
Like a -3?
If it's -3, it's going to shrink. But what if your exponent was a +3? Then it's going to grow. Nice. Have you guys, write this down. Have you heard of carbon dating? Write it down. Carbon dating. Is that growth or decay? Growth or decay? Do they use carbon dating for growth or decay? They use it for decay. So think of this. If you were to die, Morgan, let's make a graph of your death. So your body right here is day 1, it's fully intact. Now your body's not gonna grow, it's gonna decay. How fast is it gonna decay? If you look at your body 1 month on once a month, what's it gonna look like after 1 month?
It's going to decay fast.
It's gonna decay pretty fast. What about the second month?
Not as fast.
I mean, maybe that first year it's gonna decay, but then what happens in year 2? It's not gonna decay that much. So it's gonna decay pretty fast at first, but eventually, and especially 10 years down the road compared to 20, I mean, Morgan's body's not gonna change that much. So carbon dating.
How long does
That's a good question. How long does it take for a body to decay? I don't know. I don't know.
You're the math teacher here.
I like that mansion show.
Okay, let's write this down. Compound interest.
You know, the black guy.
You heard of compound interest? Okay, these are the two fields where E is going to show up all the time. E is used for carbon dating and compound interest. It's like a number. E is a number just like pi. On your calculator, who found E? Where is E? Okay, look above divide. So go second divide. There's E. Press enter. 2.71828. So if you got to round it to 4 decimal places, 2.7183. Okay, from now on out, we're going to call E the natural base. So tell me, what is e to the fourth? E to the fourth, do it on your calculator. What is e raised to the fourth power? How'd you do it, Shania? E? This E above divide?
Use the other one.
Now look at Logan found another one. Where's your other one, Logan? Look to the left of 4. You see the ln to the left of 4? E, this E is always going to be the base of some exponent. So if I want to go e to the, Shania, your way is perfect though. But e is going to be used as a power. It's going to be the base of some exponent. So e to the fourth is 54.598. And because that is used so much, everybody box this, we're going to call it the natural base. It is going to be used all the time. And we're going to call it the natural base. Alicia, what's the common base? Do you remember what the common base was? The common base was 10. So 10 squared. What's the difference between the common base and the natural base? When is the common base used? Scientific notation, right? Let's write this in. Common base, we just did the pH one. That's scientific notation. Common base is used all the time. Which one's used more, the common base or the natural base? Maybe evenly, who knows? Maybe the common. The natural base, when do we use the natural base?
When it's E.
When does E show up?
When it's the next form.
When you're doing compound interest,
Or carbon dating.
carbon dating, exponential growth or decay. That's when E is going to show up.